Hello everyone. So last time we were studying about the Hardy-Cross method, which is used to analyze or we can say design a complex pipe network. We had already done a numerical for simple pipe networks, and now we will be studying the Hardy-Cross method. So last time I already gave you a brief introduction about how the Hardy-Cross method works. I'll just repeat it again that in the Hardy-Cross method, we are usually given a loop like this, a complex a complex loop network of distribution pipes like this, in which few of the flows are available with us, and we have the k values. K values I told you that day, but we will discuss again today. You have the k values with you, and you are supposed to find out the flows through each of these individual pipes. This pipe, this, and all. Right. So in order to determine the flow through them, the chain of events goes like this, that initially you have to assume the flows, you have to select a loop, you have to assume the flows for each pipe in that loop, you need to calculate the head loss for each pipe, then you need to calculate the correction factor. So each loop has a correction factor which is applied to the assumed flow, and then by applying that correction factor to the all the pipes in that particular loop, we get the corrected flows. And if the correction factor is comparatively smaller as compared to the assumed flow, then we stop at the first iteration itself. But if, let's say, you have assumed the flow in some pipe to be 25 units and your correction factors come out to be, let's say, around anywhere between 10 to 15 units, then that's a very big correction factor which needs to be applied, and in such cases you need to do a second iteration following the same process, right? So how to calculate the correction factor, that is what we are going to see quickly. Okay, so you have this loop with you, right? And now you know the incoming flow. I'm just going to take this particular loop. The loop name is a b d. In this particular loop the incoming flow is 50. You have the k value here. Okay, so let me tell you initially about the k value itself. So k value is basically a kind of head loss coefficient. So you know, the as per the Hazen-Williams formula, head loss can be written something like this, right? And the Hardy-Cross method by default assumes that you already have the values for diameter of pipe as well as you know the pipe material. So that way, this whole equation can be represented in this way by keeping the Q, the flow, aside. And finally, this can be written like this, that since we know all these values, so this is a constant K, which is called the head loss coefficient. You have the K value, the discharge assumed, and the power is something like this, X. Now this power X may be given to you, you may have to assume it. And usually in most of the cases, this is assumed as 2. So you know the K value, right? So in this particular ABD section, ABD loop, you have given the K values 2, 1, and 2, and you need to find out the flows. So this is something like this, right? You have 50 over here. Since the K value is same for this pipe as well as this pipe, let's say we assume the flow to distribute equally. That means 25 units over here and 25 units over here. Now we have an incoming flow of 50 units from here. So total at this particular point, we have incoming flow as 75 units. So the outflow should also be equal to 75 units only, because you know, as per these law of continuity on the left hand side, the incoming flow at any junction should be equal to the outgoing flow, right? The k given here is 1, the k given here is 4, and since k is the head loss coefficient, since head loss coefficient is 4 over here, that means major head loss will occur over here. So we will provide more flow on this pipe and lesser flow on this pipe, so that even after a major head loss, there is sufficient flow available at the residential area, right? So incoming flow is 75, we will keep here 50 units, and here we will give 25 units. And also we are at this particular junction, we are given that outflow is 25 units. So incoming is 50, outflow is 25, so here it goes 25, and finally here it is given 75, and we can see it balances, that 50 is coming from here, 25 is coming from here, and it is balancing here, right? So the flow distribution is done. I'll quickly show it. Let's just write the flows. Here the flow is 25, here the flow is 50, here the flow is 25, here the flow is 25, and 25 over here, right? So this is the first thing, that you assume the flows in each loop depending upon the law of continuity. Okay, this flow, assumed flow for each pipe, can be written as QA. Coming back to the derivation part, derivation of the correction factor, I have taken the excerpts from the book itself so that we can get over it quickly. Now QA is the assumed flow. QA is the assumed flow, right? And let's say Q is the actual flow which should have been there in the pipe. Then delta, which is the correction factor, can be given as actual flow minus the Q. Q minus Q. Actual flow minus the assumed flow. That way we can write Q, the actual flow, as assumed flow plus delta, right? And now I have already given you this expression. I've already told you where it came from. So let's say the head loss in this particular case is represented by K into Q raised to power X. Now where Q is the real flow for this particular pipes which we are considering. So this can be written as this. We are basically putting in the value of Q, then K into, we are opening this particular brackets which goes something like this, and higher powers are neglected because we assume that the delta, that is the correction factor, has to be very small. Okay, so delta square will automatically be very small again. And finally we have this thing, that head loss is equal to this, right? Now we also know that the head loss, or we can say the pressure head, or we can simply say the pressure, as per the law of continuity which I just showed you above, the algebraic sum of pressure drops in a closed loop must be 0, right? So in the particular loop which we had taken, the loop ABD, as shown on the right side, in the loop ABD, the pressure drop or the pressure head or the head loss should be the summation of the head losses in each pipes of that particular loop should be 0. That is what is written over here, that summation of head losses is 0. Again opening this thing, here we can see this step, we are opening the brackets, we get like this, right? And now this delta, which is the correction factor, it is constant for a particular loop, right? For all the pipes in a particular loop, the correction factor is same. So delta can be taken out over here in the front, out from the summation. Okay, and finally we can write delta in this form. This is the value of correction factor. Further adding one or two steps more, delta can be written as this. We have taken the, basically we have taken the absolute of this value, this value. Okay, and finally we have this expression with us. So the reason for taking the absolute is given over here. So delta, we have this final formula of delta, that delta is equal to minus head loss, and the formula of head loss is already given to you, k q raised to power x, head loss upon x into summation of HL upon QA absolute. Right, this is the formula of correction factor for one loop, and similarly the correction factor for other loops can also be found out depending on whatever the head loss is there, whatever values assumed flows are there. So again, I'll just revise the steps which need to be followed while solving a numerical. You assume the flows, assuming the flows, calculating the head loss through each pipe of that particular loop, calculating the correction factor as per this formula on the right, and finally applying that correction factor to the assumed flows. Correction factor to assumed flows. You get the corrected factor, you get the corrected flow. If that correction factor is very small as compared to the assumed flow, then the numerical is solved. If not, then the numerical continues with the next iteration. Okay, and we do this particular chain of events for all the loops, and we will be seeing this in the numerical following. Okay, so this is the numerical which we have with us. We have been given a loop. Yeah. So we have been given a loop, right? We have been told that the formula of head loss is given as k into q raised to power n, right? Q raised to power x, q raised to power n means the same thing, and the value of k is given to us for all the individual pipes. Again, I have already shown you the distribution, how the distribution can be done, distribution of flows. So here it is 25 and 25. Here the incoming is 75, so we distribute accordingly 50 and 25. This is same as the earlier example. Then 25 over 25 from here, 25 from here, outgoing is 50, incoming is 50, outgoing is 25, so we provide 25 over here. And finally 50 from here, 25 from here is incoming, and outflow is 75, so that means it is balanced now. Right, now we will select the loops. So one loop is this one, right? A, B, B. The other loop is B, C, D. Okay, let's just complete the loop. We'll say A, B, D, A and B, C, D, D. Right, and also remember that you have to very carefully assume the flows along with the positive and negative sign. That means whatever flow is, whichever pipe has a flow in the clockwise direction, that is assumed to be positive, and whichever pipe is having a flow in the anti-clockwise direction, that is taken as negative flow, negative assumed flow, right? So we'll start from here. Here we assume the first loop and all the three different, just a moment, yeah. So we have the pipe section AB. For that, the assumed flow is 25, as we have already seen over here on the left. K is given to us. We calculate the head loss, right? And also we calculate the HL upon QA absolute value, if you remember the formula. So this is the formula over here of the correction factor, right? Keeping this formula in mind, we are calculating all the above parameters. We are calculating head loss and we are calculating this bottom value, numerator and denominator. Likewise, for the second pipe BD, the assumed flow is 25. It is positive because it is in the clockwise direction. K is given to us. We have calculated the head loss and we have calculated the HL upon QA. Likewise, for the pipe DA, since on left hand side with the blue pen, DA is, sorry, dA is this direction, which is anti-clockwise. So that's why the assumed flow with the direction is taken as negative. Here it is minus 25, right? K is given to us. We have calculated the head loss. We have calculated the HL by QA. Now, for the correction to be applied, we know the formula minus summation of HL. This summation has to be done along with the sign, right? Because there is no absolute, upon X into summation of HL upon QA. This is summation over here, and we have finally the value as this minus 2.5. So this is the correction which needs to be applied to all the assumed flows of the pipe. So this 25 minus 2.5 goes to this 22.5. Likewise, minus 25 minus 22.5 goes as, sorry, minus 25 minus 2.5 goes as minus 27.5. And for this particular pipe, as of now, 25 minus 2.5 is again 22.5, right? But why it is showing as 35, we will see after we have done with the next loop. Okay, now I'll just give you the hint that since this particular pipe on the left which I am representing, this is common to both the loops, so the correction factors for both the loops will be applied on it along with the signs. Okay, moving forward, for the next loop BCDP, this particular loop, we have again three sections: BC, which is 50, which is positive, CD and DB, which are all in the anti-clockwise direction and hence negative, minus 25 and minus 25. We have the K values with us, we have the head loss with us, we have the HL by QA value with us. We apply this correction factor formula and we finally get the correction factor as minus 12.5. Okay, and this minus 12.5 is applied to all these. Here it goes, here it goes, and for this particular pipe we will specifically see now. Sorry, for BD DB here we will see. And now look carefully that, let me just draw it once. If this is the loop, and this is BD, and the flow in this BD is something like this, then when we are looking at the first loop, here the flow, that 25 is in positive direction, right? So that's why we apply the correction as 25 minus 2.5. Okay, and here when we are looking in the second loop, this is in the negative direction where the correction is minus 12.5. Now this correction being minus 12.5, when both the loops are combined in this form, then we get that 25 minus 2.5, and the correction factor for other loop will change. That minus 12.5 will become plus 12.5, and we will have the final as 35. Or else you can also do like this, that starting with the second loop where the flow in BD was minus 25, okay, correction was minus 12.5, and the correction for this left loop was minus 2.5. We will change the sign, we'll keep it as plus 2.5 now, since it is being considered in the second loop. We get as minus 35. So whatever you assume, the answer is numerically going to be same. And the signs are different because of the clockwise and anti-clockwise position of the particular flow in both the loops. Okay. Now we are done with the first iteration for both the loops. If let's say the loop had been a bit more complex, would have taken all the other sections again. Just a minute. Yeah. So now assuming the corrected flows which we have obtained, these are the flows which we have obtained till now. Assuming that these corrected flows are the assumed flows for the second loop, second iteration, sorry, we will continue again with the first loop, with the second loop, and here we see that the correction factor comes out to be very small. minus 2.7 and minus zero point 0.3. So whatever flows we achieve at the end of this particular iteration, we will stop over there and we will say that these are the flows, these are the flows almost near to the true value, which will be occurring in the pipes, which will be occurring in the pipes of these particular loops, right? And we had to repeat the iteration because here the correction factor was minus 2.5, which was okay, because minus 2.5 as compared to 12.5 is, it's okay, not much of a correction factor. But for the second loop, it was minus 12.5, and when we compare it with, even if we compare it with 50, which is the highest value, it is approximately 25%, right? Which is not good. So that is why we had to repeat the iteration, and now if we compare it, it is very small. Okay, so we'll stop over here. And I'll just mention again that there is another criteria which you can see, that initially for the first loop the correction factor was minus 12.5, now it is minus 2.7, so it is almost similar. That means we can stop since the correction factor is not changing much. This maybe you can also look at, right? So you can try some other numericals also which are given in the book, and the notes for which have already been uploaded in the files section. And that's it for the class.